I'm R. Prabha, Assistant Professor in the Department of EC, SNS College of Technology. In this video, we are going to see the topic Faraday's Law and Displacement Current. This is for the course Electromagnetic Fields. So, the topics we have discussed earlier are based on electrostatic and magnetostatic fields. So, this electrostatic field is due to stationary electric charges, and the magnetic fields are due to motion of electric charges with uniform velocity or due to magnetic charges. But in this topic we are going to study about time varying fields. So these time varying fields are produced due to time varying currents. So the Faraday's law was given by British physicist and chemist called Faraday, and he is a great experimental scientist. His contribution to early electricity include invention of motor, generator and transformer, electromagnetic induction and also laws of electrolysis. And according to Faraday's law, a static magnetic field cannot produce any current flow, but the time varying field an electromotive force EMF induces which may drive a current in a closed path circuit. And this EMF is nothing but a voltage that induces from changing magnetic fields or motion in the conductors of the magnetic field. So Faraday discovered that the induced EMF is equal to the time rate of change of magnetic flux linking in the closed circuit. So according to his law, he wrote about the EMF E is equal to minus n into d phi by dt. Here n is number of turns in the circuit, E is nothing but induced EMF. Suppose if n is equal to 1, it is a single turn circuit, we can write the EMF expression as E is equal to minus d phi by dt in volts. So here negative sign indicate that the direction of induced EMF is such a way that it produces a current which will produce a magnetic field oppose the original field. And according to Lenz's law, the induced EMF acts to produce an opposing flux. And considering Faraday's law, the induced EMF is a quantity which is measured in volts, and it is given by E is equal to integral over the closed path E dot dl. That is the line integral of electric field intensity over a closed path. So this closed path such that if any part of the path is changed, the EMF will also change. So the magnetic flux is denoted as phi passing through certain specified area is given by phi is equal to integral of B dot ds. So here B is equal to magnetic flux density. So we already know that E is equal to minus d phi by dt according to Faraday's law. Here phi is the flux linkage and it is replaced by surface integral of B dot ds. So by combining the equations we can write the induced EMF E is equal to integral over the closed path E dot dl, or it is equal to minus d phi by dt B dot ds. So from the Faraday's law we can go through two conditions. One is the closed circuit in which EMF is induced is stationary and the magnetic flux is sinusoidally varying with time. So from the previous equation of this EMF, that is E, the only quantity which is varying is called the magnetic flux density. So we can write the integral of E dot dl is equal to integral of minus dou B by dou t dot ds. And this is similar to transformer action, and this EMF induced is called transformer EMF. And we know that this, according to Stokes theorem, we can easily replace the line integral by surface integral. So in equation 6, the left hand side term integral of E dot dl can be replaced by integral over the closed path del cross E dot ds. So this is replaced according to Stokes theorem, and which is equal to the right hand side term minus integral over the surface area dou B by dou t. So here we are assuming both the surface integrals are taken over the identical surfaces. And removing the integrals, we can write that del cross E dot ds equal to minus dou b by dou t dot ds, and removing this ds, we can write del cross E is equal to minus dou b by dou t. And this is one of the Maxwell's equation, and curl of electric field is equal to minus dB by dou b by dou t. Here B is the flux density, magnetic flux density. And in the case of electrostatics, E dot dl is equal to 0 because the electric field is not vary with time, so del cross E is equal to 0. And the second case, the magnetic field is considered stationary and constant, which is not varying with time, but the closed circuit is revolved to get the relative motion between them. So this action is similar to generator action, and this EMF is called generator EMF. And the force is taken as F, and it is given by F is equal to Q V cross B. Here Q is the charge, V is the velocity, B is the magnetic flux density. So the motional electric field intensity is defined by as force per unit charge, and it is given by EM is equal to E by Q. So by dividing Q, the motional electric field intensity is V cross B. V is velocity, B flux density. And the induced EMF is integral over the closed surface EM dot dl. So we can also write right hand side term as integral over the closed surface V cross B dot dl. And here this E is equal to BLV sin 90 degree. We know sin 90 degree is equal to 1, so it is called BLV. And here L is length of the straight conductor. So integral of E dot dl in the third case, flux density is also varying. Then induced EMF is the combination of transformer EMF and generator EMF. So E dot dl is given by minus dou b by dou t dot ds plus V cross B dot dl. So this is the third case. And next we come for displacement current. So Faraday's experimental law has been used to obtain one of the Maxwell's equation in differential form, that is del cross E is equal to minus dou b by dou t. So this says a time varying magnetic field produces an electric field. And according to Ampere's circuital law, we know that del cross H is equal to J. And by taking divergence on both sides, we get del dot of del cross H is equal to del dot of J. So we know that del dot of J is equal to minus dou rho v by dou t. Here rho v is called charge density. So we can conclude that del cross H is equal to J plus G, and by taking the divergence again, we have 0 on the left side is equal to del dot J plus del dot G. So finally this del dot G is equated to dou rho v by dou t, because del dot J is equal to minus dou rho v by dou t. So here we conclude del dot G is dou rho v by dou t, and this G is given by dou d by dou t. We know dou is the field flux electric flux density. So finally we can write the Ampere's circuital law in point form. It is del cross H is equal to J plus dou d by dou t. So this is one of the Maxwell's equation, and here J is called the conduction current density, dou d by dou t is called displacement current density. So the magnetic field is equal to two types of current densities. One is conduction current density and displacement current density. And this displacement current density JD can be written as dou d by dou t. But we know that the current density J is equal to sigma into E. And also with respect to charge density, we can write the current density J is equal to rho v into V. So by concluding everything, we can write del cross H is equal to dou d by dou t, since J is equal to 0 for non-conducting medium like air medium. Thank you.